Hello, this is Bruce Wallenberg, and this is Lecture 4 in our series on power generation, operation, and control. We'd like to point out that this lecture is not necessarily about power systems. This is about the mathematics of optimization. And we're going to give you actually several lectures now about optimization topics before we pick up the topic of economic operation of power systems. This one is about continuous and differentiable functions. So if we start here with a function like this, it's a function of two variables, x1 and x2. If I set f equal to 2, then all the points x1 and x2 that can give you a value of 2 look like this ellipse here. If I set it equal to 1, then I get this ellipse here. So these ellipses represent the function f. This is the you could look at this something like a map with contour lines. So this is the contour lines of this function. We're going to try to minimize that. Where is x1 and x2 that reach a minimum? So we'll take and we'll do the normal thing we do in calculus, differentiate each one with respect to the first variable x1, set it equal to 0, do the same with the second variable. If we stack up those two derivatives, we come out with what's called the gradient, or del f. This is the symbol for del f, the symbol for the gradient, and we want to get it to 0 and 0, which means the minimum. Well, it turns out, of course, the derivative here is 0.5x1, so that's 0 at 0, and this one is 2x2 is 0, again at 0. So the optimum, very simply, is down here. The minimum is down here. So if you want the minimum of the function itself, it's right here at the origin. Okay, now we're going to make the problem a little bit more complicated. In fact, we're going to put a constraint called omega, and that constraint is a straight line, but you always want to write this as omega equals 0. See, what we're saying is 5 minus x1 minus x2 equals 0. And that's this straight line like this. And what we would like to do now is we want to minimize this function, our objective function, while maintaining omega equals 0, which means that we're only allowing the points that are on this straight line, that are where I'm running the cursor up and down here, the pointer up and down. Those are the only points allowed. Now, if I had a larger ellipse out here or a larger one out here, we would see that these points intersect at larger numbers than 5. I mean, we might have one for 6, and we might have one for 7, and so forth. And where they intersected would be different, and we'd like to reach the minimum value of f that's along this line. So we're looking for the minimum f along that line. And it's going to occur, not surprisingly, where it is tangent to the line. That is where the minimum value will occur. And that happens to be at x1 equals 4 and x2 equals 1. Now, if you take the gradient of f, and here I'll draw the gradient of f up here at this value, f equals 6, notice that it points in this direction like this. It is perpendicular to f at this point. This is the gradient with respect to omega, and it is also perpendicular here, but these two vectors do not line up. They do not line up. Therefore, this point is not an optimum. And if you look at it, you can say, well, if I can go a little bit lower down here, I can get a smaller value of f, and this vector will start to bend over. If I go way down here, once again I'm perpendicular to f and I'm perpendicular to omega. They don't line up. At the optimum, those vectors line up, and this is what the French mathematician Lagrange realized, was that he could use this property to mathematically solve the problem. And it simply said, I have a gradient function and I have another gradient over here, and these are vectors, and so if I take the gradient with respect to f and the gradient of omega and I just multiply one of them, in this case we'll always multiply the constraint function, if I multiply it by a scalar. So lambda is always used in this context for Lagrange, and that's why we use the Greek L or lambda. It's a scalar. It's just one single number, and all it does is adjust the length. And it says if I adjust the length of this, I can add it to this and get 0, or in effect I'm really getting, this should be a 0 with a line under it. It's a vector. In our case it's this vector. So if I want to get the 0, 0 vector, I can adjust just the length of omega. Now that means they have to line up. It just means that whatever the value of omega is, I have to adjust it a little bit to get it to cancel out the gradient and give us a sum of 0. So what we do then is we form something here. Again, we use this big script L. This is the Lagrange function, where we add our objective plus the constraint multiplied by our scalar. Now we've only got one constraint, so we're just using one lambda here, a scalar. Notice now that I have 1, 2, and I have added a third variable. I don't know the value of lambda. So I've now got a function with an extra variable, so I now have 3 variables. And so we just treat this Lagrangian the same way we would in calculus. We're going to take the derivative with respect to x1 and the derivative with respect to x2 and the derivative with respect to lambda, set them all equal to 0, and we'll solve our problem. So we'll do this. We'll put the function in there. There's our objective, there's our constraint, and there's the lambda right here. And we take the derivatives like this, and so you get when you take x1, you get 0.5 x1, and here you get minus lambda. Here you get 2x2 minus lambda, and you get, when you take the derivative of lambda, you always get this constraint function back. So here we have what? We have 3 equations, right? 3 equations, and I'm just going to say 3 unknowns. 3 unknowns, and the unknowns are x1, x2, and lambda. Now, this set of equations can be solved if you want to put them into a matrix and invert the matrix. If you want to run that, that certainly can be done on your calculator or on your computer. A simple way to do it here is to simply say, well, x1 has to equal 2 times lambda. x2 has to equal 1/2 times lambda. And so now I say 5 minus 2 lambda minus 1/2 lambda, and then I can solve for lambda. So I can do that just by substituting. And then when I've got lambda, I can go back and get these. And remember, we said that the solution was at x1 equals 4, x2 equals 1, and now we know the value of lambda. So that's how we solve it. That's how we mathematically solve the problem, in this case with one equality constraint. If I have several equality constraints, okay, then I would have to set the problem up like this with lambda 1 times omega 1, lambda 2, omega 2, and so forth. And I have to do the same solution again, except that now I've got two x's, x1 and 2, and I got 3 lambdas. So I got 5 variables, 5 derivatives, and I can solve the problem again. Notice that these equations do not have to be linear. They do not have to be linear. They could be nonlinear. Okay, they could be nonlinear. But then when you go to solve it, it gets to be even more difficult a little bit, because you won't have linear equations anymore to plug into this, and finding the solutions, and there may be multiple solutions. Let's leave that for now. Now the next is to talk about inequality constraints. So we've done one where we had omega equals 0. Well, in this case, I've got a constraint that says g of x1 and 2 is less than or equal. I'm always going to use that, never a greater than constraint. You can always convert them over. So less than or equal. And what it means is if any points out here are considered violating, and we say that's the infeasible region. Infeasible means you don't meet the conditions of the constraint. So I can't have any points out here in this range where I've got it cross-hatched. I can have points on the line or anyone over here. So everything in here is okay. So anything in this direction is okay. Those points, and that we say that's the feasible region. Now this extends out, on a straight line all the way to infinity or whatever you want. But we just know that above the line is infeasible, below the line is considered feasible or okay. It does not violate the constraint. So now I have a problem that says minimize this, meet the condition of a number of equality constraints, and meet the condition of a number of inequality constraints, where x is just a vector. Well, when we've done this, we end up with something that's a much more complex problem to solve. And the mathematics for this was originally done by these people. Originally, much of the world recognized the work of the mathematicians Kuhn and Tucker, but later on discovered that there was another mathematician named Karush, and had done earlier work, so they honored him by calling this what we call the Karush-Kuhn-Tucker conditions. Sometimes you will just hear these referred to as KKT. Okay, KKT, these conditions. And here's what they are. So let's say we develop a Lagrangian again, an objective plus a set of Lagrange multipliers lambda times omega. These are functions that are all equal to 0. And then we have different Lagrange multipliers designated as mu. And we have these functions g, which are less than or equal to. Now, at the optimum, so we'll give it this superscript 0 over here as the optimum of this problem, meets minimum of the function, meets the equality constraints, and meets the inequality constraint. So the first thing is that the derivatives with respect to the x's are all equal to 0. All partial derivatives with respect to the x's are equal to 0. The derivatives with respect to the lambdas give us back this omega. So every omega that's an equality constraint is equal to 0. I just say that derivative gives us a restatement of the constraint condition. When I take a derivative with respect to mu, though, I get the g condition that says it's less than or equal to 0. However, the Karush-Kuhn-Tucker conditions require that we look at a fourth condition called the complementary slackness condition. And what it says is for every mu and its respective g function, the product of mu and g equals 0, and mu is a number, it's a scalar that's either equal to 0 or greater than 0. And what this means now is that this is the complementary slackness condition, and we're just going to look at it. Either mu equals 0, that'll give you 0 up here, or g equals 0, that'll meet this condition, or both are 0. Okay, that's an unusual condition. It's usually one or the other of these. And obviously, if mu equals 0, that means that g is not 0. Okay, it's not 0, and it's therefore not binding. You know that when we said g is less than or equal to 0. Well, if g equals 0, that means we're right up against the constraint. If g equals 0, so let me put that over here. We say if g is equal to 0, okay, then we call that binding. That's binding. If g is less than 0, then it's not. I'm just going to say not binding. Okay, I won't write that all the way out. Not binding. So this means binding means it's right up against the constraint. If it's less than 0, well, that means it's not binding, and the points are, as it were, they're in the feasible region, but they're not up against the constraint. Okay, and we know that when mu is 0, we are not binding. That means that this condition up here is met because mu equals 0. If we're in a constraint where it and then of course pardon me, if mu equals 0, then this can be some number that's not binding. If mu if g is binding, if g is binding, then mu can be a number greater than 0, and usually is. Okay, and it usually is. So let's take add another g constraint. Here's our g says that it's another linear function less than or equal to 0. And here's g right here. This is our line w over here. And we originally solved and said, well, if you're just minimizing with respect to this objective and you want it meeting that equality constraint, there's the minimum. However, now this one says this function has to be less than or equal to 0. Well, if you think about it, if these numbers, let's say x1 and x2 are way out at 5 or 10, then this would be a large number, and the whole value over here would not be less than or equal to 0. So this region out here to the right of that line is the infeasible region. Can't have any points out here or they violate this. You can have a point that's on the line or back over here, back out this way. It's okay as far as that constraint is concerned. So what we're looking for then is the minimum of the function, and it's got to be on the g function, or else it's got to be in the feasible region, and it's got to be on the omega. And what we do is we're going to go ahead and show you the logic using that complementary slackness to solve the problem. Our Lagrangian now has the original objective in x1 and x2. It has lambda times the omega function, mu times this. How many variables now? 4 variables. 4 variables, or 4 unknowns. Now, here they are. Here's the objective. Here's omega. Here's the g function in here. I take derivatives with respect to x1 and x2, and I get this. I get minus lambda plus mu. Here I get minus lambda plus 0.2 mu. So that's in these two derivatives. And then I get the second Kuhn-Tucker condition is this one that's the omega condition. And the third gives me the g of x function out here. This is my inequality constraint, and the fourth condition says mu times this equals 0, and mu must be greater than or equal to 0. Now, we know how to test for a solution being optimum, but we don't know exactly how to get there. So what I'm saying is we can start out and we could say, okay, let's try this, and is that an optimum? Well, we can test it, but we don't know exactly how to get to the optimum. And the reason is because this mu value, we don't have an exact way to solve for it here. So what we're going to do is we're going to say, okay, set mu equal to 0. Then by conditions 1 and 2. Well, mu equals 0 says that g of x can be any old value. We're back to our old minimum again here, 4, 1, with x lambda equals 2. But at 4, 1, we have a number here, 4 plus 0.2 x2 minus 4 was the other 2 times x. X1, here it is, 0.2 times x2 minus 3, we get 1.2. Well, that's not less than or equal to 0. So this function, this solution is no good at mu equals 0. So now I'm going to say, okay, let mu equal be greater than 0. And then I can just say, well, okay, if mu is greater than 0, then I know that both constraints are binding, so I can just use those constraints to solve for x1 and x2. I get a different solution. And then I can go back to condition 1 and I can solve for lambda and mu. And it turns out now that g is exactly 0 when we use 2.5 and 2.5. So all the conditions are met. We've solved for all 4 conditions of the gradients with respect to x1 and x2, the derivative with respect to lambda, meaning that the omega function is okay, and so is the g function satisfied down here. So we've satisfied it. So this is the solution to that problem.